Welcome to the session on cloud computing and its application. In today's session, we will talk about module number 4, chapter number 8. In particularly, we will talk about technologies for data intensive computing. Data intensive computing concerns the development of applications that are mainly focused on processing large quantity of data. Therefore, storage system and programming models constitutes a natural classification of the technologies supporting data intensive computing. So when we talk about technologies for data intensive computing, two broad classification has been made. One is on storage system and second one is on programming models. Traditionally, database management system constitutes the default storage support for several types of applications. Due to the exposure of unstructured data in the form of blocks, web pages, storage logs, and sensor readings, the relational model in its original formation does not seem to be the preferred solution for supporting data analytics at a large scale. So what is the reason for change in the storage system? That is, earlier that was relational RDBMS. What factors contributed to this change are growing of popularity of big data, growing importance of data analytics in the business chain, presence of data in several forms, not only structure, as previously mentioned. What constitutes relevant information today exhibits a heterogeneous nature and appears in several forms and formats. Structured data is constantly growing as a result of the continuous use of traditional enterprise application and system. But at the same time, the advances in technology and the democratization of the internet as a platform where everyone can pull information has created a massive amount of information that is unstructured and does not naturally fit into the relational model. New approaches and technologies for computing and cloud computing promises access to the massive amount of computing capability on demand. This allows engineers to design software systems that incrementally scale to abruptly degree of parallelism. It is not rare anymore to build software applications and services that are dynamically deployed on hundreds or thousands of nodes, which might belong to the system for few hours or days. Classical database infrastructure are not designed to provide support for such a volatile environment. High performance distributed file system and storage cloud. Distributed file system constitute the primarily support for the management of data. They provide an interface where to store information in the form of files, later access them for read and write operation. Among the several implementation of file systems, few of them specially addresses the management of huge quantity of data on a large number of nodes. Mostly, these files constitute the data storage support for large computing clusters, supercomputers, massively parallel architectures, and lately storage computing clouds. In that, first one is Lustre. The Lustre file system is massively parallel distributed file system that covers the need of a small workgroup of clusters to a large scale computing cluster. The file system is used by several of the top 500 supercomputing systems, including the one rated as the most powerful supercomputer in the June 2012 list. Lustre is designed to provide access to petabytes of storage to serve thousands of clients with an input-output throughput of hundreds of gigabytes per second. The system is composed by a metadata server containing the metadata information about the file system and a collection of object storage servers that are in charge of providing storage. Users access the file system via a POSIX complaint clients, which can be either mounted as a module in the kernel or through a library. The file system implements a robust failover strategy and recovery mechanism, making server failures and recoveries transparent to the clients. Second one we have under high performance distributed file system and storage cloud is IBM General Parallel File System, GPFS. GPFS is the high performance distributed file system developed by IBM, providing support for 6,000 supercomputers and Linux computing clusters. GPFS is a multi-platform distributed file system built over several years of academic research and provides advanced recovery mechanism. GPFS is built on the concept of shared disk, where a collection of disks is attached to a file system nodes by the means of some switching fabrics. The file system makes this infrastructure transparent to the users and strips large file over the disk arrays also by replicating portion of the file in order to ensure high availability. By means of this infrastructure, the system is able to support petabytes of storage, which is accessed at a high throughput and without losing consistency of data. Compared to other implementation, GPFS distributes also the metadata of the entire file system and provides transparent access to it, thus eliminating a single point of failure. Third one we have is Google File System, GFS. GFS is the storage infrastructure supporting the execution of distributed application in the Google's computing cloud. The system has been designed to be a fault-tolerant, high-availability distributed file system built on commodity hardware and standard Linux operating systems, rather than a generic implementation of a distributed file system. GFS specially addresses the need of Google in terms of distributed storage for applications, and it has been designed with the following assumptions. The system is built on top of the commodity hardware that are often fails. The system stores a modest number of large files. Multi-GB files are common and should be treated efficiently. Small files must be supported, but there is no need to optimize for that. The workloads primarily consist of two kinds of reads: large streaming read and small random reads. The workload also have many large sequential writes that append data to files. High sustained bandwidth is more important than low latency. These are some of the assumptions made while building a Google file systems. Next we have Amazon S3. Amazon S3 is the online storage service provided by Amazon. Even though its internal details are not relieved, the system is claimed to support high availability, reliability, scalability, infinite storage, and low latency at commodity cost. The system offers a flat storage space organized into buckets which are attached to an AWS account. Each bucket can store multiple objects, each of them identified by a unique key. Objects are identified by unique URLs and exposed through HTTP protocol, thus allowing a very simple get-put semantics. Because of the use of the HTTP protocol, there is no need of any specific library for accessing the storage system, whose object can also be retrieved through BitTorrent protocol. Despite its simple semantics, a POSIX like client library has been developed to mount S3 bucket as a part of the local file system. Besides the minimal semantics, security is another limitations of S3. The visibility and the accessibility of the objects are linked to AWS account, and the owner of the bucket can decide to make it visible to the other account or public. It is also possible to define authenticated URLs, which provides basic access to anyone for a limited period of time. BitTorrent is a point-to-point file sharing protocol used to distribute large amount of data. The key characteristics of protocol is the ability to allow user to download a file in parallel from multiple hosts. One more type which comes under high performance distributed file system and storage cloud is sectors. Sector is a storage cloud supporting the execution of data-intensive applications defined according to the Sphere framework. It is a user space file system that can be deployed on commodity hardware across a wide area network. Compared to the other file system, Sector do not partition a file into blocks but replicates the entire file on multiple nodes, allowing the user to nodes, customize the replication strategy for better performance. The architecture of the file system is composed by four nodes. First one, a security server. Second one or more master node. Then we have slave node. And fourth one, we have client machines. The security server maintains all the information about access control policy for user and file, while master coordinates and serves the input output request of the client, which ultimately interacts with the slave node for accessing a file. The protocol used to exchange data with the slave node is UDP based data transfer protocol, which is a lightweight connection less oriented protocol optimized for wide area networks. In the second category, we have not only SQL system, there is NoSQL. The first one which I have seen was high performance distributed file system and storage clouds. Here, next one we'll see not only SQL, that is NoSQL systems. The term NoSQL was originally coined in 1998 to identify a relational database which did not expose a SQL interface to manipulate and query data, but relied on a set of unique shell script and commands to operate on text files containing the actual data. In a very strict sense, NoSQL cannot be considered a relational database since it is not a monolithic piece of software organizing the information according to the relational model, but rather is a collection of scripts that allow user to manage most of the simplest and more common database tasks by using text files as information store. Later in 2009, the term NoSQL was reintroduced with the intent of label all those database management systems that did not use a relational model but provided simpler and faster alternatives for data manipulation. Nowadays, the term NoSQL is a big umbrella and all the storage and database management system differs in some way from the relational model. The general philosophy is to overcome the restriction imposed by the relational model and to provide more efficient systems. This often implies the use of tablets without fixed schemas to accommodate larger range of data types or avoiding joins to increase the performance and scale horizontally. Next we'll see the broad classification of NoSQL. First one is document stores. Second one is graphs. Third one we have key value stores. Fourth one we have multi-value database. Fifth one we have object databases. Next, tabular stores. And finally we have tuple stores. These are some of the broad classification of NoSQL. Under this, we will be studying couple of few types. Prominent implementation supporting data intensive computing. In that first one we'll see Apache CouchDB and MongoDB. Document stores, both of them provide a schema-less store where the primary object are documents organized into a collection of key value fields. The value of each field can be of type string, integer, float, date, or an array of values. The databases expose a RESTful interface and represents data in JSON format. Both of them allow querying and indexing data by using the MapReduce programming model. Exposes JavaScript as a base language for data querying and manipulation rather than SQL, and support large files as documents. From an infrastructure point of view, the two systems supports data replications and high availability. CouchDB ensures ACID property on data, whereas MongoDB supports shredding, which is the ability to distribute the content of a collection among different nodes. The second one we have is Amazon Dynamo. Dynamo is the distributed key value store supporting the management of information of several of the business services offered by Amazon. The main goal of Dynamo is to provide an incremental scale and high availability storage system. This goal helps in achieving reliability to a massive scale where thousands of servers and network components built an infrastructure serving 10,000 millions of requests per day. Dynamo provides a simplified interface based on a get-put semantics where objects are stored and retrieved with a unique identifier, that is the key. The main goal of achieving an extremely reliable infrastructure has imposed some constraint on the properties of these systems have. For example, ACID property on data have been sacrificed in favor of a more reliable and efficient infrastructure. This creates what is called an eventually consistent model, which means that in the long term, all the users will see the same data. The slide showing the figure of Amazon Dynamo architecture. The architecture of Dynamo system shown in figure is composed of a collection of storage peers organized in a ring, sharing the key space for a given application. The key space is a partitioned among the storage peers, and the keys are replicated across the ring, avoiding the adjacent peers. Each peer is configured with access to a local storage facility where original objects and replicas are stored. Also, each node provides facility for distributing the updates among the ring and to detect failure and unreachable nodes. With some relaxation of the consistency model applied to replicas and the use of objective version, Dynamo implements the capability of being an always writable storage where consistency of data is resolved in background. The downstream of such approach is the simplicity of storage model, which requires application to build their own data model on top of the simply built block provided by the storage. For example, there are no referential integrity constraints. Relations are not embedded in the storage model and therefore joint operations are not supported. These restrictions are not prohibitive in case of Amazon services for which the single key value is acceptable. Next one we'll see is the Google Bigtable. Bigtable is a distributed storage system designed to scale up to petabytes of data across thousands of servers. Bigtable provides storage support for several Google applications, exposing different types of workload from throughput-oriented batch processing jobs to latency-sensitive serving of data to end users. The key design of big data are wide applicable scalability, high performance, and high availability. To achieve these goals, Bigtable organizes the data storage in tables whose rows are distributed over the distributed file system supporting the middleware, which is the Google file system. From a logical point of view, a table is a multi-dimensional storage, multi-dimensional sorted map indexing by a key represented by a string of arbitrary length. A table is organized into rows and columns. Columns can be grouped in common family, which allows for specific optimization for better access control, the storage and the indexing of the data. Client applications are provided with very simple data access model that allows them to address data at column level. Moreover, each column value is stored in multiple versions that can be automatically timestamped by Bigtable or by the client applications. Besides the basic data access, Bigtable APIs also allow more complex operations such as single row transactions and advanced data manipulation by means of a Swazwal script language or the MapReduce APIs. Swazwal is an interpreted procedural programming language developed at Google for the manipulation of large quantity of tabular data. It includes specific capability for supporting statistical aggregation of value read or computed from the input and other features that simplifies the parallel processing of petabytes of data. The diagram showing the architecture of Bigtable architecture. Here, system monitoring and data access is filtered through Chubby, that is also responsible for managing replicas and provide consistency among them. At the very bottom layer, Data is stored in a Google file system, GFS, in the form of files, and all the update operations are logged into the file for easy recovery of data. In case of failure or when tables need to be reassigned to the service. Big data is the result of study of requirements of several distributed applications in Google. This server also it serves as a storage backend for 60 applications such as Google Personalized Search, Google Analytics, Google Finance, Google Earth, and manages petabytes of data. In the diagram shown, Bigtable identifies two kinds of processes, master process and table server process. A table server process is responsible for serving requests from a given tablet, that is contiguous partition of rows of tables. Each server can manage multiple tables, that is from 10 to 1000 common. The master server is responsible for keeping track of the status of the table server and of the allocation of table to table servers. The server constantly monitors the table to check whether they are alive. In case they are not reachable, allocated table are reassigned and eventually partitioned to other servers. Next one we have Apache Cassandra. Cassandra is a distributed object stored for managing large amount of structured data spread across many commodity servers. The system is designed to avoid a single point of failure and offers a high reliable services. Cassandra was initially developed by Facebook and now it is a part of the Apache Incubator initiative. Currently, it provides storage support for several large web applications such as Facebook itself, Dig, and Twitter. Cassandra is defined as a second generation distributed database that builds on the concept of Amazon Dynamo, which follows a fully distributed design, and Google Bigtable, from which inherits the column family concepts. The data model exposed by Cassandra is based on the concept of table that is implemented as a distributed multi-dimensional map indexed by a key. The value corresponding to a key is a highly structured object and constitutes the row of the table. Cassandra organizes a row of a table into columns, and sets of columns can be grouped into common families. APIs provided by the system to access and manipulate the data are very simple: insertion, retrieval, and deletion. The insertion is performed at the row level, while retrieval and deletion can operate on the column level. In terms of infrastructure, Cassandra is very similar to Dynamo. It can be designed for incremental scaling, and it organizes the collection of nodes sharing a key space in a ring. Each node manages multiple and discontinuous partition of key space and replicates their data up to n nodes. Replication uses different strategies, and it can be rack away, data center aware, rack unaware, meaning that the policies can take into account whether the replication need to be made within the same cluster or the data center or not to consider the geolocation of the nodes. As in Dynamo, node membership information is based on gossip protocol. Cassandra also make use of this information diffusion mode for other tasks such as dimensioning the system control state. The local file system of each node is used for data persistence, and Cassandra also makes extensive use of commit logs, which makes the system able to recover from the transition failure. Each write operation is applied in memory only after it has been logged on the disk so that it can be easily reproduced in case of failure. When the data in memory transpasses a specific size, it is dumped to the disk. Read operations are performed in memory first, then onto the disk in order to speed up the process. Each file includes a summary of keys it contains so that it is possible to avoid unnecessary file sharing to search for a key. Last one we have is the Hadoop HBase. HBase is the distributed database supporting the storage need of the Hadoop distributed programming platform. HBase is designed by taking inspiration from Google Bigtable, and its main goal is to offer real-time read-write operation for tables with billions of rows and millions of columns by leveraging clusters of community hardware. Internal architecture and logic model of HBase is very similar to Google Bigtable. An entire file system is backed by the Hadoop Distributed File System (HDFS), which mimics the structure and services of GFS. So, in this section, we discussed the storage solution supporting the management of data-intensive application and especially of what is referred as big data. Traditionally, database, mostly like to be based on the relational models, have been the primary source for handling large quantity of data, but due to the unstructured data, relational database became not practical and provide poor performance. Alternate to that, all these different distributed file systems has come into picture. So in today's session, we have talked about the technologies for data intensive computing. All the contents has been taken from the textbook Mastering Cloud Computing written by Rajkumar. In the next session, we will talk about programming platform